All right, so this is, yes, just an overview of computer vision and then its applications to robotics, as well as I hope to go into, how would you get started, because the field, the latest and greatest research in the field is very complicated. There's a lot of math, but there are some places where you can get started with open source libraries and so on, and do a few fun things with robots that can see. And then, of course, I'll have references, textbooks for you to read. So the first question I sort of wanted to ask was, is the Kinect a big deal? Is it important? What the heck is this thing? How does it work? Because it's in the news lately. They're using it for video games, and that doesn't seem to me the best application of computer vision, but it's a marketable one. So essentially, it has an IR projector in it. It fires an IR laser through diffraction grating, and that turns into many points of IR light, a grid of IR light. It's a structured light scanner, which is different from a time-of-flight scanner that would measure the time it took for an IR beam to travel to and come back to the wall or to an object that it hit. It was interesting researching this because nearly every tech blog got that wrong, and the first comment on every tech blog article about the Kinect is, that's wrong, it's not a time-of-flight scanner, it's a structured light scanner. So this grid of dots of IR light, if something is closer, the grid will be deformed, and it looks at the deformities in that grid and then gives the programmer, using the API, a depth map of each point in the image, its approximate depth, just a grayscale depth map. So it can be used as a relatively cheap, sorry?
Just a quick question.
Yeah.
Particular positions of points of light, are they like pre-calibrated at the factory or something like that?
They're just a regular grid pattern. Of course, the farther away your wall is, the more spread out they'll be. But it essentially looks at the distortion of that field. Yeah, it's just a regular grid. Jimmy?
Did you say it was laser, IR laser?
I believe so.
You know it's harmful for your eyes.
It's
not something-
no, it's
iSafe.
It's iSafe. It's what, tier 1 or level 1, however they rate them. Yeah, it's definitely safe for your eyes. I mean, I'm not about to test that by getting my eyes up close to one, but it's the main thing about it is that it's cheap. It's poor quality, poor resolution, but it's a very cheap sort of 3D scanner. You could make potentially a 3D scanner out of 2 or more Kinects, although the grid meshes will interact with each other. They'll interfere with each other if you try that. But some people, that's true, and some people have gotten relatively good 3D maps so you can walk all the way around the room without too much shadowing. Yeah, so it's not a revolutionary concept. The really important thing about it is that this stuff is getting cheaper. It's getting much easier because you get, there's the output essentially that you get a depth map. This is provided by some of the Windows drivers people have managed to make on the Kinect. Main thing about it is it's making this sort of thing very accessible. You can get one of these maker bots. I think I saw one of these in someone else's slide today. And you can get a Kinect, a maker bot, and you can reproduce things. You can scan and then print things. That kind of thing is fun to do. And now hobbyists can do that.
You mean I can make a bobblehead or something?
Pardon? Yes.
Exactly.
Yeah, you could exactly. That's exactly what you could do. So let's talk a bit about robots. The applications of vision to robots. Alex over here obviously has a robot that can see the line and tries to follow a line that way. Here's a picture. It's got lines that have been figured out by an algorithm. It's trying to find the road so that it can follow a road. And they can interact with their environment because everything doesn't have to be hard-coded if they can see what's going on around them. And then, of course, they can also shave. So I don't know if you trust a robot to shave you yet, but this is an example. Maybe I'll build a robot that's a chia pet that shaves itself. But if we have time later, we can look at the paper, more examples, more pictures of people being shaved by robots. So of course, this is more of interest to forensic specialists. I've got a picture of someone who robbed a store. I want to see maybe what he'd look like if he shaved, and then when he goes through the TSA scanners, we can nail him even though he shaved his face. It'll still match. Something like that. Another big complicated application of computer vision might be reconstructing the interior of a building from images. The exterior of buildings, we've been seeing, Google Maps, Google Earth, trying to put 3D models of cityscapes and so on up online. But building interiors are much more complicated. There's a group I can show a video later. We'll get to the end, but plenty of videos I could show of the results of them having, having various photos of a room taken from different points, and they can actually put together a 3D reconstruction of the room, and then apply the images onto, as textures onto the 3D model. And so, just in terms of computer vision in general, we can see if we look at how they do this. They have a processing pipeline. It's kind of, the reverse maybe of a rendering pipeline for graphics or something. You get the images and go through various steps to analyze them, process them, and then reinterpret them in a different way. Quite a few applications. There's a robot used for quality control on assembly lines by Stobley Unimation, and so that can detect various objects that are being produced on the assembly line, and then if it doesn't recognize something, or if it recognizes a part has been deformed, it can flag it, that can be tossed out, and so on. Medical imaging is probably the big, one of the biggest areas for computer vision to be really useful, and image processing especially, and just examples off the top of my head, if you're writing an object tracker, you could use that to guide missiles. Next, we can talk about, now we can start getting less of a broad concept. What is computer vision? Robots could see. That would be useful. But if you wanted to get started and do something with that yourself, I would recommend, before you pick up one of the big textbooks that used to be on the back wall there, using an open source framework like OpenCV, Open Computer Vision stands for, and I'm sure there are others. OpenCV is a huge library with lots of functionality. I know Mark has a mixed opinion of its use, but as a starting point, if you want to get started, I'd recommend it. You can give it individual images and process those. You can work with sets of images, like a bunch of images in a room, try to reconstruct the room in 3D, or you can work with a live video feed. And one thing that we did in the lab here was manage to get various image processing working on an iPhone. You could also equally easily probably do it on an Android or BlackBerry. You want something with decent amount of processing power, especially if you're going to do this on a live video feed. But then there are plenty of places you can go with that. Line following robot, good example. Measuring environments. There was a presentation yesterday on odometry using cameras, trying to measure the distances between various points. And of course you can recognize objects. Face recognition is a popular example. And then you can do something with that. Here's an image I found, reference in the top left corner there. Just an overview of OpenCV, which, like I say, is its huge library. It has a bunch of math libraries that they think are useful to in the context of computer vision. It has some robot support, and then it's got all this stuff in the middle there. It even has various machine learning algorithms that are used to tune computer vision algorithms, the processing functions. And then it does all kinds of things. Segmentation, which is trying to determine what objects are separated from one another, so on and so forth. Tracking, trying to follow something as it moves. Some easy starting points, things that don't require a lot of know-how, a lot of math to just get working. If you use OpenCV, you can pass it an image and say, return me an array of all the points where there's a face. And it just does it. You don't need to know how that's done, but face detection can be done with it. Contour detection and edge detection, trying to find out what objects are separated from each other. Edge detection is kind of interesting. You can do that simply by applying a couple convolution filters to an image. So that's kind of an interesting example. You can do that with hardware accelerated API like OpenVG. I know I've done edge detection with that, and you don't need a framework or anything. That's kind of a fun exercise. And more complicated things are to use stereo images, get a 3D representation or to try to find the structure of something from the motion of the camera. There's a link up at the top I could click on. We could talk about this more in depth, but this is kind of a complicated algorithm, but the essential way face detection is happening when you call that function in OpenCV is that it's looking for these HAR features, named after the guy who created them, that are just a bunch of rectangles, white and black. It goes through the image and compares the average dark and light regions of pixels in an area, and then it looks for patterns that represent a face. So your forehead is usually much lighter than what's below your forehead, so it overlays one of these HAR features that would be a white bar and a black bar over top of your face, over top of the image until it finds something that matches, looks like a forehead with something underneath it. The same for your nose